The terms molar mass and molecular weight, they literally refer to the same thing. They're referring to the total mass of all of the atoms in a molecule. So if you're asked to calculate the molecular weight or the molar mass of a molecule, given its formula, all you have to do is add up the masses of all of the individual atoms in that formula. The masses of each atom, as you probably remember, come from the periodic table. So in this particular molecule, we can see that we have 6 carbon atoms. That means we need to take the mass of 6 carbon atoms. The periodic table gives us the mass of 1 carbon atom, 12.011 grams. Your periodic table might have like slight differences in the decimal places on these atomic masses, and that's okay. We have 8 hydrogen atoms in this molecule, and the periodic table tells us that each hydrogen atom has a mass of 1.008 grams, and then we have 6 oxygen atoms, and each oxygen atom is 15.999 grams. So all we have to do is just add this up. 6 times 12.001 plus 8 times 1.008 plus 16 times 15.999. Not 16. 6, not 16. 6, I'll have to start that all over. 6 times 12.001 plus 8 times 1.008 plus 6 times 15.999. 176.124. The units on this are grams per mole. So this is telling us that 1 mole of this molecule, C6H8O6, has a mass of 176.124 grams. And we can use this relationship, the molecular weight, to allow us to convert between moles and grams of this particular molecule, vitamin C. That's what we'll do in problem number 2. It's asking us how many moles are there in 5.75 grams. 5.75 grams of vitamin C. To convert that into moles, we want to put the units grams of vitamin C down on the bottom, so that those units can cancel out. We want to convert into units of moles of vitamin C, and to do that, we're using this relationship, the molecular weight, which tells us that 1 mole is 176. I'm just going to leave off that 0.124, 176 grams. 5.75 divided by 176 is 0.0327 moles of vitamin C. If we are being asked to calculate how many molecules there are, that's just going to take one extra step at the end of this problem. So we'll start by converting our grams of vitamin C into moles, just like we did in problem number 2. 1 mole of vitamin C is 176 grams of vitamin C. And then, since that's not what we're being asked to do, we need another step. 1 mole of vitamin C is 6.022 times 10 to the 23rd molecules. So using Avogadro's number, 0.86 divided by 176 times 6.022 times 10 to the 23rd. This is 2.94 times 10 to the 21 molecules. And question number 4 is actually really similar, asking us how many individual hydrogen atoms there are in 3.2 kilograms. At first you might think, I don't have any idea what I'm supposed to do here, but that's okay. You know, with all of these problems, you know you're going to need to start by writing the number and the unit that's given to you. So 3.2 kilograms, I'm going to abbreviate VC for vitamin C. Now, the kilogram unit is not super useful in these conversions. All of these conversions that we're doing are between grams and moles. So that means step 1 should be to get rid of that kilogram unit. 1 kilogram is 10 to the 3rd grams of our vitamin C. And once we have converted ourselves into, wow, I don't know how I came up with that, VC. Once we've converted into our grams of vitamin C, our next job is always going to be to convert into moles. So 1 mole of vitamin C is 176 grams of vitamin C. And actually, instead of vitamin C up here, I'm going to use the molecular formula. C6H8O6. That's actually going to be helpful. C6H8O6, which is vitamin C. So cancel those units out. So what we've done here is figured out that's how many moles we have of vitamin C. And the next thing that we want to do, actually the next step you take kind of depends on like your personal preference here. But what I like to do next is convert that vitamin C, 1 mole of C6H8O6, convert that into molecules, just like we did in problem number 3, 6.022 times 10 to the 23rd molecules of that C6H8O6, C6H8O6. And from the molecular formula tells us that there are 6 carbon atoms in every molecule. There are 8 hydrogen atoms in every molecule. That's what we're actually looking for, that 8 hydrogen atom. So we can use that like a conversion factor. 1 molecule of C6H8O6 has 8 atoms of hydrogen. And that is a lot of steps, but that's how we're going to get this to atoms. So now we just need to work out all of that math. 3.2 times 10 to the 3 divided by 176 times Avogadro's number, 6.022 times 10 to the 23rd times 8. This gives us 8.76 times 10 to the 25th atoms. Now, the last problem on here, initially it's going to look like it's different than the others, but it's actually using the same type of strategy. This problem is asking us to determine the empirical formula of a compound that is 43.9% carbon, 7.3% hydrogen, and 48.8% oxygen. First of all, the empirical formula is just the ratio. In this case, it's the ratio of carbon to hydrogen to oxygen in terms of moles. So it's going to be the ratio in terms of units of moles. And what we've been given to start with is the percentages, which is the ratio of the carbon to hydrogen to oxygen in units of grams. So 43.9% carbon means 43.9 grams of carbon, 7.3 grams of hydrogen, 48.8 grams of oxygen. So again, the data that we're starting with is the ratio of carbon to hydrogen to oxygen in units of grams, and the empirical formula, what we're trying to figure out, is going to be the ratio of carbon to hydrogen to oxygen, but in units of moles, not in units of grams. So all we have to do is convert all of these into moles. We'll do that using the gram to mole conversion. Grams of carbon, we are right here, and just to kind of like save space, I'm going to round that mass of carbon. I'm just going to call it 12, just to kind of save space. 1 mole of hydrogen is 1 gram of hydrogen. That's on the periodic table. And then for oxygen, 1 mole of oxygen is 16 grams of oxygen. So we can get rid of our periodic table, and we're just going to see what we get here. Now, sometimes, occasionally, when you do this, convert from grams to moles, everything's going to work out perfectly. This is going to be 3.7 moles of carbon, 7.3 moles of hydrogen, and 48.8 divided by 16 is 3.0 moles of oxygen. So in some instances, when you do this mole to mole to mole conversion, everything works out perfectly, although that's pretty uncommon. What we figured out right now is the ratio is 3.7 to 7.3 to 3.0. We've figured out that the empirical formula is this, which is not normal way for us to communicate empirical formulas or molecular formulas. These numbers need to be integers. Some people are going to be tempted to just round these, and you shouldn't do that. They should work out to be closer to integers. You shouldn't have to round that much. Like 3.1, I'd feel good about rounding that to 3, but a 3.7, it's a little bit far off. So what we're going to do to kind of make this math work out we're going to look at these numbers that we have. We're going to pick the smallest of all of these numbers, and we're going to divide all of them by that small number. This way, we're not changing the ratio of these numbers. The ratio is going to stay mathematically the same, but what we're trying to do here is to just sort of convert these into better looking numbers. So we get a 1.2 and a 2.4 and a 1. 1.2 moles of carbon, 2.4 moles of hydrogen, and 1 mole of oxygen. And the numbers still aren't looking very good. A lot of times after we do the division, like these get fixed and they look really nice, but not always. So when you get to this point and they're still not integers, the next thing you have to do is multiply. And this is kind of a guess and check situation. So what you're going to do is just start by multiplying everything by 2 and see what that gets you. That's going to get you 2.4, 4.8, and 2. Still not integers, which means multiplying by 2 was not the right thing to do. Back up out of that and try multiplying everything by 3 and see what you get there. Now that's still not going to work out because we can see that the carbon is still not an integer, still not looking good. So that means 3 is not right. Let's back out of that and let's try multiplying everything by 4. It doesn't always take this many steps. Like this is feeling like quite a lot of steps, starting to make me a little bit nervous, like maybe I crunched a number wrong. If you're feeling uncertain about this, like maybe I've messed up, you can always go back and double check your work, or you can just kind of keep plowing ahead and see what you get. So multiplying everything by 4, still not looking good. Let's try multiplying everything by 5. And if you're really good with decimals and like seeing decimals as fractions, that makes these problems easier. You don't have to go through the process of guessing and checking quite so much. Because if you're really good with math and decimals, you might have right away seen exactly what we needed to do. You might not need to go through that whole process, and that's cool if you have that ability. So it looks like we found the right number. Multiply everything by 5, and if we multiply everything by 5, what am I doing here? Then these work out to be perfect integers, and that's what we're looking for. We're looking for these kind of perfect integers. This is a process that kind of reminds me of balancing equations. Sometimes it feels like it's just getting worse and it's never going to solve itself, and then all of a sudden it just works out. So this tells us that the empirical formula is C6H12O5.